Okay, we're back, and we're going to do some E&M. And in this case, this is one of my favorite problems to give students as a challenge problem. This is actually from 1998, and with my students, I tend to call this the hardest problem ever. It's a Faraday's Law problem. It has to do with magnetism, magnetic flux, electromagnetic induction, and it looks something like this, where a bar is sliding down a hill through a magnetic field, and you have this closed loop on top, which is a little circuit, and it has some of the usual things that you get with these types. Find the current, which way is the current going. In this case, we're going to have a magnetic braking type force, so your speed is going to be changing, and so on. So we're going to kind of take this and use it as our example. And let me switch over here. So this is one of the cases where we have Faraday's Law. Faraday's Law says that whenever you change the magnetic flux, and how quickly you change the magnetic flux, you induce an EMF. Okay, that's electromotive force, which is a voltage. Voltage turns on, currents turns on, forces turn on, all this weird stuff starts to happen. So in this case, we have a version where the magnetic field is constant and the area is changing. And in my diagram, this reddish area is where you have flux. So as this bar moves down the hill, that area is increasing. Okay, so that's our situation. The good news for something like this, for any case, any kind of problem, any situation or picture where the area is changing, we can ask the question, what area are we talking about? Well, it's that red area, it's that little rectangle. So we have the time derivative of the length of the bar times the x that I have on this other side, the side on the hill. Okay, that's just the area of that rectangle. Now as the bar slides down, the only thing changing is the x length. The L length, the length of the bar, doesn't change. And so what we see is that we get the voltage, this induced voltage, is the magnetic field times the length of the bar. The x dt is just your speed. Okay, your speed down the hill. So this expression is what you always get in any of these situations. Okay, now we could ask, well, what's the current? Currents we're always going to get through Ohm's law. So this induced voltage divided by the resistance. I'm not going to worry about that minus sign. We just want the number of amps. So BLV over resistance will be our current. We can use Lenz's law to figure out the direction of the current. Is it going to be going clockwise or counterclockwise? Well, in this case, we have an increasing flux coming out of the hill. The area is increasing. Okay, so Lenz's law says that the induced EMF, the current, the new magnetic field are going to go in the opposite direction of the existing magnetic field. It wants to stop the increasing flux from happening. So if we use our curly right hand rule, we need our thumb to go into the hill, and that means that the current in this loop is going to have to flow around like this, in a clockwise direction. Now, what this means is that if you look at the bar, in the bar, let me clean this up and get this couple things out of the way. The current that's induced is flowing that way, kind of like towards us or to the left in our picture. Now we have a consequence of that. Whenever there's a current inside a magnetic field, there's a force acting on it. Now if we do the IL cross B, okay, if we think of the right-hand rule, the current is kind of like coming towards us. That would be our thumb on our right hand. Our fingers are pointing up in the direction of the magnetic field. okay, going through the hill. That gives us an uphill force. Okay, so there's a magnetic force that goes uphill. That's going to try to slow us down. Now our force diagram, not only do we have this magnetic force going uphill, but we have downhill mg sine theta. We've got gravity. So if we look at Newton's second law on the bar, the acceleration is down the hill. Okay, so this mg sine theta is going to be a positive force. This magnetic force, okay, IL cross B, is going uphill, trying to slow us down. Okay, now let's take the magnitude of our current. Okay, we get to substitute that in to the ILB. I'm going to solve for the acceleration. Divide through by the mass. We have g sine theta minus, we're going to have a b squared L squared times velocity. And that's all going to be over the resistance. Then we divide through by the mass. We'll have the mass down there too. Okay. Now our goal is, one of the things that they asked in this problem is, what's the velocity as a function of time? Okay. Well, to get time into the mix, we're going to have a differential equation. Acceleration is dv dt, okay, the rate of change of velocity. So this is the equation that we get. Now, this is also mathematically the same as air friction. Okay, when a skydiver jumps out of a plane. In that case, the acceleration of a skydiver is, well, they're free falling, so you have gravity going down, and then you have the air friction force going up, okay, opposite the motion. So these are mathematically the same. Okay, I'm going to go through and solve this thing fairly quickly for time's sake in this video, but we have to separate the variables. Okay, so I can bring time up on the right-hand side, and then if I divide through by everything in the parentheses here, we should be able to integrate this thing. Okay, let me change colors here. The limits on our time typically are just going to be start the clock at some point. That's our 0 time. Okay, maybe when we start the bar off. Okay, or we can even start it at rest. So speed-wise, we could start it at rest, and what we're trying to find is that final speed. Okay. Well, over here on the right-hand side, that's just our time interval. Over on the left, we have the natural log of g sine theta minus these constants times v, and we're going to have to evaluate that. Okay. Now, because of the chain rule, this coefficient here in front of our variable, in front of the velocity, we need the reciprocal of that to come out. Okay. Now it becomes all algebra. I'm going to, again, I'm not going to do every single step here, but when you evaluate this on the left, we're going to have the natural log, where you plug in v final, subtract what you get when you plug in v initial, and it'll look something like this when I simplify it. Okay, and I'm going to bring those constants over on the right-hand side. Now's a case where I can, like I like to say, I can e both sides to get rid of the natural log. So the first term is just going to be 1. The second term is going to be a little more complicated. We're going to have b squared L squared over mr g sine theta, okay, times the final. And now we have an exponential term over here. Okay. Again, we're trying to solve for v final. And so when I do that, okay, remember where we started. We start up here with, this is all coming from Newton's second law. V final is going to have, we're going to have a funny looking constant out front. And then we're going to have 1 minus this exponential term. Okay? This is your velocity as a function of time. It looks like a mess when it's symbolic like this. But conceptually, this is a terminal velocity. If we look at our velocity as a function of time, when time is 0, we'll have in parentheses 1 minus 1. It starts at 0, that's cool. That was our initial condition. As it accelerates down the hill, it reaches a maximum speed as the exponential terms approach 0, where your maximum speed, according to this, is the same as your terminal velocity. It's a constant, and that's that thing up front. Okay, that's the terminal velocity. Now we could have got the terminal velocities from right up here, from F equals ma. Terminal velocity means that there's no acceleration. So if we solve this for v, look at what we get. These two terms in here would be equal to each other, so your v is going to be mg times resistance sine theta all over b squared L squared. Okay, so that matches. That matches in our solution. Okay, so that's all fine and good. So yeah, it's a variation on a theme. Generally, when you have these types of problems, when something's changing like the area, we know what to expect when we get our voltage, we know what to expect when we get our current, we know there's going to be a braking force. Okay, any situation where the area is changing. F equals ma in this case, because we have gravity, we have a constant force in addition to magnetic braking force, you're always going to get a terminal speed. The math is just kind of nasty looking here, but we've done it before for skydivers, and now it's coming back to haunt you. Okay, just a slightly different picture. So the math is all the same. Okay, so if you need to review this as often as you need to, keep in mind going through this derivation here, you might want to try to do the algebra yourself. Okay, fill in the math that I kind of skipped over. Again, I did that for time's sake. And see if this makes sense at all. Okay, I hope this helps. It was kind of a weird problem. Again, it's from 1998, and on my website you can find the full-blown solutions. You can look at those step by step if you want. Whatever works. So, again, I hope this helps. Until next time, we'll see you later.